for today, and we're going to be talking about distance triangles a little bit more. I'm going to recap a calculation that a few students asked me about in web courses in homework one, just to reinforce it. And I'll try to do that every once in a while. If something gets a lot of people tripped up on homework, I'll try to reinforce it and stuff in the next lecture. Okay, here's our SI schedule. So right after class, 12:30, Nelson School of Communication, room 114. Yeah, right down the street here. All right, so go ahead and do that. Now, today's the last day of practice questions um, and bonus point activity. And Tuesday next week, we'll start accumulating official participation. That's why I want to try to get the registration thing all ironed out. And if need be, I'll make sure everybody's got a bunch of bonus points. I'm not going to be like a, you know, you know, what's that? Simon Legree. I'm not going to be, ultra tough about that. Try to get them sorted out. So anyways, that's in web courses that you want to do that. Um, now, if we dismiss a little bit early, and even if not, and if you have a question, you did get your bonus points and stuff, and if you don't have to dash off to class right after this, let's just meet out in the hallway. I'll sit in the chair, and you know, you can sit next to me, and we'll kind of work on your iClicker situation, and just takes a second, and we'll get that done. Okay, so does that sound good? No, your neighbor. Okay, does that sound good after class? Question over here. Question over here somewhere. Who had a question? I saw a hand go up. Did you have, you didn't have a question? Okay, let's keep going. Okay, homework recap. The one that I want to go over is this one, the North Icelandic jet. And that's actually a diagram from a journal called uh, Nature Geophysics. And they, discovered this new current in the North Atlantic, the North Icelandic jet. It's in red here. So, and I used it as a context for a fairly simple calculation of speed. But there's a couple things, let's blow this up a little, a couple things in here that I want to go over. And this is an instance of this calculation problem that I uh, that I previewed this morning. Every time you encounter a calculation problem in this class, in web courses, where you have to type in, some numbers, 2.35 or whatever, and then hit the submit, submit the quiz. Every attempt is going to have a randomly assigned value for the distance or the mass or for, at least one of the numeric factors that you use is going to be randomly revalued in your next attempt. So you have to read them really carefully. All right, so this one, I say that so that you realize that you might not have seen 3086. This one, it says, in that time, the swimmer has moved 3,086 meters. Now, you might have had 29,017 or 2,917 or 1,805 or some combination thereof, some other value. Okay, but this is the one we're going to work on today. All right, so here we go. And you might want to jot down some notes. So we're going 3086 meters in an elapsed time of 30 minutes. And what we want, the task is to get an average speed to the nearest 0.1 meter per second. All right, so the first thing you got to do, and I think I caught a bunch of you napping on this, and not that I was trying to, catch you napping, but I think a few of you forgot to convert from minutes to seconds. All right, so let's make that our first task. So jot this down. 30 minutes, 60 seconds per minute. So just multiply that number by 60. and that'll be the number of seconds. And that goes in for your elapsed time, delta t. All right, so 1800 seconds. All right, now you're ready to use the average speed formula, delta S over delta T. And just so you realize, um, I use delta S as a generic direction. Because if you look at this diagram, it's on the globe, it's on a sphere, it's on a sphere of the Earth, and it's actually kind of moving northeast. So, and I didn't specify the northeast axis or anything. So, so for any direction, uh, I use the symbol S for some generic axis or generic direction. Anyways, so there's our generic formula for. So now you plug in your values. Numerator that was already given, 3,086 meters, and now down the denominator, 1,800 seconds. And I think a bunch of you got caught with 30 minutes in the denominator. Not sure, but I saw a few numbers that were way off. Not close, but way off. So if you put in 30 minutes down there, you're going to be way off. Anyway, so there's your calculation. And now you calculate. You go to your calculator. And this one has 1.7144 repeating. So I just wrote out a few digits of that. But if you look up in yellow at the top of the screen, it says get the average speed to the nearest 0.1 meter per second. All right, so we don't need all those other decimals. So my answer is going to be just the first two numerals there. But wait, there's more. At the bottom of the problem, right before you type it in, there's this little blurb. It says type in the numeric part of your answer to the nearest 0.1 meter per second. All right, so I'll always do this. On a problem like this, I'll always specify, give me to the nearest 0.01 meters or to the nearest 0.1 meter per second or whatever. And the reason I have to do that is because I don't want you to type in meters per second. All right, so I have to specify the number and only the number because web courses can't handle, like you type it in meters per second. All right, not easily anyways. So we're just going to type in the numeric part. So what's the numeric part? Well, to the nearest tenth of a meter per second, it's just 1.7. And that is the number that you type in. All right. For this instance of problem 5. Now, if you started out with, everybody had 30 minutes. And the swimmer has 30 minutes, and the distance changes each time. So you might have 2903 or something like that meters in your next attempt. All right, so you take that 1.7 and you type it in down here. And then you do your other questions, the multiple choice and stuff. And you submit it, and then when you see it, you see that you got 2 out of 2 if you did it this way. All right, so remember that. We're going to have a ton of problems like this through the semester. And also, every homework assignment, the minimum is going to be 4 attempts. And the reason for that is I want you to use them as study tools. So burn 1 attempt, then go study, review your notes if you got something wrong, and go try the second attempt. And you'll always have 4, and sometimes I give you a second shot. Like I might, if I decided to, I could give you a second shot in homework 2 on the North Icelandic jet problem, okay? So that would be effectively another 8, a total of 8 attempts on that one. Sometimes I give an entire assignments if it's got a lot of calculations in it, and you'll have some that are like that. I might give it 7 attempts. And sometimes students, talk to me in web courses and discussions, Dr. B, how do you do this, acceleration calculation on homework 4 or whatever it happens to be? And we'll have a little discussion in discussions, and I'll coach them along. And um, they end up asking me, boy, I wish I hadn't used up all my attempts. So what I sometimes do is go in um, before the due date, so like over the weekend, I see a student, man, I wish I had some more attempts. I'll go in and reset it to 7 attempts or something like that. So everybody gets another, because sometimes they're tricky. This one's not particularly tricky, especially now that you know how to do it. So be aware of this, and as I say for my exam questions and homework, read and clicker questions in class, read carefully. Don't breeze through casually. Read carefully. All right. Now I want to do some clicker questions with you, so go ahead and get those babies out. Um, and if you haven't used your clicker yet, let me see. You should be on frequency DD, and you should get a Go Nitro message. And if you don't get the Go Nitro, that means you're not on the right frequency. All right. And if you're not on the right frequency, the way to fix that is to hold down the power button until the rectangle in the upper left flashes, and then you type in DD. And that'll get you the Go Nitro message because we're on frequency DD. Now, in this regard, I'd like to point out something to you. We've been using the physics definition of average velocity, delta x over delta t, and remember, or average speed. And remember, it doesn't really tell you if all you're doing is an average, point 1 and point 2 and an elapsed time, you don't know what's happening necessarily between point 1 and point 2. Like the hare and the tortoise. The tortoise just keeps going along, but the hare is doing all kinds of different things. So if all you know is the average speed, you don't really know too much about intermediate times. But it is an average speed formula, okay, and it's useful in its ways. There's another more generic formula for getting averages of things outside of physics. So let's think about that for a second. And here's a set of 4 measurements. Go ahead and jot those down in your notes. Get your calculator out. All right, and then these are just, you're measuring brownies in your mom's kitchen before they get devoured. All right, and so you measure the long side, 2.8 centimeters, whatever, 3.0 centimeters, 2.92. They're all about the same size. Okay. So here's the question: how would you calculate an average? Go ahead and raise your hand if you have a. Okay, young lady over here in the middle. Yeah. Yeah, add them up and divide by 4. Okay, so go ahead and make a note of that. All right, now that'll work for any kind of, add them up and divide by how many. That'll work for an average. And there's other average, there's averages using calculus and stuff. But they all boil down to basically this. So, um, so here we go. Here's the first clicker question. All right, question number 1. Which of these is actually a formula for average speed? I want you to read very carefully. Under the generic concept we just talked about. Add them up and divide by how many? All right, 10 seconds to vote, starting now. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, let's see what you guys voted for. Yeah, pretty good. Um, Looks like most of you got it correct. Correct answer is B. And now we're going to take that concept and we're going to build on it. But before we do that, I want to do a very simple demonstration. Um, I need a volunteer from the audience, but it has to be a person that has a skateboard. Anybody have a skateboard today? Okay, you're up. All right, take your skateboard and your Yeti hat. Nice. Top of the aisle. Okay, and Sean, can you move this table out of the way? Just move it over here. That's good. Okay, now what's your first name again? Elsie? Kelty? Kelty with a T? Oh, S-E-Y. Okay, Kelsey with an S. Okay, Kelsey. What we're gonna do? What we're gonna do is what? Why are you giving me the bird? Uh, all right, Kelsey's at rest right now. She's not moving. Okay. Kelsey, take one foot up onto your skateboard but don't start yet. Okay. Okay. 1 foot and 1 foot on the ground to keep you. Now she's going to start at rest. If she's at rest, what is her speed? 0. Okay. And Kelsey, what I want you to do, it's very simple. Just blaze down here to the bottom and stop. Go ahead. Okay, thank you. All right. So that's it. That's all we needed. So she's definitely got a bunch of speed down here at the bottom of the ramp or the bottom of the aisle. But she started with zip zap up on top. All right, so let's think about that. Next question. Read carefully and make a vote. Okay. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, yeah, most of you guys got this one right. V is equal to 0. All right, now we're going to use that um, and go ahead and make a sketch. Here's a ramp that we're going to talk about for a few minutes. All right, and this is the skateboarders up at the top of the and at rest up here at point P1, and then at point P2 down here, down by the first row. Um, we don't know the speed, but it's definitely positive, 3.4 meters per second or something like that. Okay, so V2 is a positive number, and V1 is 0. All right, now. Next logical question, back to the idea of average speeds. All right, and we still got the same ramp. So here's question 3. Get my cursor, come on. Here we go. Okay. If V1 is equal to 0.0 meters per second at point P1, How does the average speed formula add them up and divide by 2? How does it simplify? Go ahead and make your decision. 10 seconds to vote. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, and most of you guys got that one correct. There's your simplification. Now we're going to use that, so make a note of that. The average is half of what the skateboarders got at the bottom of the run. All right, so whatever that is, you know, you get your radar gun out and you measure their speed, you zap them at the bottom of the run. Half of that is the average speed, okay, just by token of this formula. All right, so there we go. Now, we're going to analyze the acceleration. So along the ramp, the skater's accelerating. All right, so acceleration, that's delta V over delta T. All right, and another way of saying that, if you're going to analyze the acceleration, is to say that delta V is equal to A delta T. That's the same as the definition of acceleration is A equals delta V over delta T. This is the formula for how much speed you get under acceleration for a certain amount of time, delta T. All right, so, but it's based on the definition. It's basically A equals V delta T and then cross multiplied. So now the delta T is over on the side with A. All right, so now delta V in this context is V2 minus V1. All right, so that's, and I'm switching to simplify notation. I'm switching from delta T just to regular T. Okay. So V2 minus V1 equals AT. All right. Now we haven't used our average speed result yet up there in the red rectangle, but we're gonna use it. All right. So let's get rid of that little blurb there. All right. Now, side note, at point P1, the skateboarder's at rest, so V1 is equal to 0. All right, we already know that. That was one of the previous clicker questions. So that's good. Now, what that helps us do, go ahead and write down on the next line how this form, let me get my cursor over here. How would this formula simplify under this side note? Go ahead and write it down, underneath there. And I'll do the same. I'll give you a second to think about it. How would this formula here simplify if V1 is equal to 0? All right, go ahead and write it down. Yeah, how does this formula, where my cursor is pointing right here, the second formula down in the equation block on the right, how would that simplify if V1 is equal to 0? All right. So I'll give you a chance to think about that. How many of you got this? V2 is equal to AT. Good. Yeah, why, it's simplified. Why do you even write V1 at all? If it's 0, just, leave it out. So that's nice. All right. And V2 is equal to AT. So the speed, if she starts, so here's a sentence that expresses the same thing. If the skateboarder starts from rest, her speed at the end of the run is the complete effect of acceleration. All right, AT. A times the elapsed time, T. All right. Now, let's use the average speed formula. All right. So we know if we've got acceleration from rest, V2 is equal to AT. All right. And V2 is the numerator up here in the average speed formula. All right. So let's slap that in there. So instead of V2, let's write down AT in the numerator of the average speed formula. All right, so this is the atom up and divide by 2. V1 is 0 in this one, so it doesn't appear in the average, in the rectangle over here on the left. And V1 is equal to 0. It drops out of this baby and simplifies into V2 equals AT over here on the right-hand side. So we're using this idea of starting from rest to our advantage. All right. And hopefully you can see something shaping up here. Because now, let me get rid of this curly Q. Now we can write this down. Go ahead and write this. This is our equation that we talked about last week. The distance is equal to the average speed times delta t. Good old speed times time. That's the formula used for the Icelandic North Icelandic current problem, except you're trying to figure out the average speed in that. Okay, but so distance equals speed times time. Nice. All right. So what that means is, all right, speed times time. So AT over 2 times delta t, or in this case t. So well, here's what we've got. The distance of the skateboarder's travel along the aisle, ramping downwards, is according to the average speed formula here at the bottom, AT over 2 for the average speed, times the amount of time that you're at average speed. All right? And guess what? That simplifies to 1/2 AT squared, which is what we talked about last time. That is the distance rectangle result that we talked about on Tuesday. All right, so let's get it all put together. All right. Well, let me pause first though. Any questions about the steps here and how it all kind of ties together? Yes, go ahead. Yeah, and the point is that this formula down here, 1/2 AT squared, we already derived that from remember 1/2 base times height, okay? And it's also traceable, its ancestry is also traceable back to distance equals speed times time if you have average speed. So when we did the distance triangle in the velocity graph, we didn't talk about average speeds, okay? But if you do talk about average speeds like this, yeah, it also synchronizes. It all hooks up. Yeah, but since it works in that context, you can then make a fancier formula in case you don't have, in case you don't start from rest. And actually, we've already seen that. Remember that on graph paper, the really fancy one, YF equals YI plus, you remember that? That was on, I think it was first or second day. That's actually, that's the Y coordinate equation under free fall, G, with some initial upward speed or downward speed, either way. So yeah, you can do a little fancier formula. This is the way to get it to be fairly simple looking. And so then you would say, well, okay, let's make a little fancier, more general equation, not from rest, and you can handle it. Another question. Okay, let's bring them all together. All right, so the distance under acceleration formula, the simplest version. So this is like dropping something from the roof of the library, dropping a water balloon, or the supposed uh, the story about Sir Isaac Newton. He discovered the law of universal gravitation because an apple fell out of an apple tree and conked him on the head, and he started thinking about it. Now, why did that happen? Okay, so that was, the apple starts at rest and then falls and conks him on the coconut. All right, so that formula comes from the distance triangle um, concept in the velocity graph. This is the one that we did on Tuesday. All right, we started with distance rectangles, and those were cinchy. Distance rectangle, constant speed, same speed all the way through. And the area of the distance rectangle is just width times height. And but for acceleration like this, it's 1/2 base times height. The other thing is the distance formula, d equals 1/2 at squared, also comes from definition of acceleration and distance at average speed formula. So the distance at average speed formula is delta x equals v bar, average speed, times delta t. All right, so either one of these, if you analyze them, and these are separate analyses, all right, so one proceeds from the velocity graph idea and a fairly simple interpretation of the area between the velocity graph and the time axis. So this is the area. The triangle that I've got shaded in there up there it represents the distance, or the area of that triangle represents the distance that something travels in 1 second of free fall. Hey, you guys, how far would that be? 1 second of free fall. 1/2, and the acceleration is negative 9.8 meters per second squared times 1/2. Let's see, 1 second squared is 1 second squared. And then 9.8 meters per second squared. So you have negative 9.8 meters. Second squareds cancel. And then, so you're down 9.8. But then you got to calculate the 1/2. So then because it's 1/2 gt squared for that distance rectangle. So I see somebody breaking out their calculator. They're checking me out. 9.8 divided by 2. What do you got? Yo. Yep, 4.9. Okay, so and it's negative 4.9. So you're 4.9 meters below the roof of the library in 1 second. All right. So if you drop that water balloon, and I think the library is probably going to be, let's see, how far would it go in 2 seconds? Let's see. 2 seconds, quantity squared is 4. 4 times 9.8 is 36. 39.2? Is that correct? Verify me. 4 times 9.8. 39.2. Okay, so 39.2 times 1/2. So what is that? 19 point. So is the library 19.6 meters tall? That's about 60 something feet, maybe. We'd have to go up there and do some experiments and time the water balloons. If the right person's walking down below on the sidewalk, you get to have a little fun. Anyway, so this is kind of a nifty result for us, and it shows how, sometimes, you can think about the same thing, free fall distance, accelerated distance, from 2 different directions sometimes and get to the right result. All right, so remember that. Now, let's summarize what we know. Professor Galileo, let's give a report, a verbal report to Professor Galileo. Okay, constant velocity, delta x equals v delta t. No problema, we've got that. Okay, and the velocity graph is a horizontal line segment, either above or below the time axis. If it's below, that means you're moving to the left because you're in the negative velocity territory. If it's above, you're moving to the right. All right, so that's good. And the distance rectangle is a walk in the park. All right, length times height. And the height is your speed v, and your width is your delta t. So bing, there you go. All right, now let's talk about accelerating systems. All right, and we just figured that one out. 6 ways from Sunday. All right, 2 ways from Sunday. So if you start from rest, initial speed vi, v subscript I equal to 0, which is what we did with the skateboarder demonstration. Or if you, and here's a caveat. If you come to a stop, if you start out at a positive speed and you lose 9.8 meters per second, so like a vertical pop-up on the baseball diamond, you start out with, like 20 meters per second of upward speed, and it goes straight up, losing speed all the way, and at the top, it's lost everything, okay? And you can compute that distance, all right? So if it comes to a stop, VF equals 0, yeah, delta X or delta Y if it's a baseball pop-up, 1/2 AT squared. Or if it's a baseball pop-up, 1/2 GT squared, 9.8. So, and in this case, the velocity graph is a sloped line segment. And if it's sloped down to the right, that means you're either slowing down upward speed or you're acquiring downward speed. If it's sloping up to the right, that means you're speeding up to the right, or you're losing leftward speed. That's the other way to think about that. So if you send somebody over this way at, like at the end of a long rubber band, and you send them out this way, eventually they're going to slow down to a stop. Okay, that would be sloping up to the right, but it would be below the time axis. So the distance polygon for the accelerating systems is a distance triangle. And let me move this out of the way here. So we have 2 different distance polygons. And one of them's fairly cinchy, the distance rectangle. And the other one's not too bad. It's not too shabby, the distance triangle from acceleration. Right, so there's our verbal report to Professor Galileo. But Professor Galileo, he's a bear cat. He's very tough. I mean, if we were in his class, oh my goodness, he'd be really peppering us up with questions and stuff. So here's something that Professor Galileo might want to know. What if the velocity doesn't change uniformly? The distance triangle only works if you have a constant acceleration, 9.8 meters per second squared downward. Anywhere from the top of Mount Everest to the bottom of the Mariana Trench. If you're on the surface of the Earth, that's what, up on the moon, it's about 1.6 meters per second squared downward. And if you go to the various NASA websites, you can look up the surface gravity for Mars, Mercury, Venus, all the planets. The moons of Jupiter, even, we know those. The moons of Saturn, stuff like that. We know all that stuff. But what if the velocity doesn't change uniformly? And a good example of that, as I've mentioned before, is a spacecraft or a rocket. Rocket launching over at Kennedy Space Center. It gets upward acceleration because the rocket engine's burning off the fuel. But the fuel goes out the back end, and it's not part of the rocket anymore. All right, so the mass is decreasing as it generates thrust upward. And so if it's lighter and lighter and lighter, the same amount of thrust gives it more and more acceleration. And they can throttle the rocket motors to get, to smooth it out and stuff. And that's a lot of the difficult parts of, launching those things is a complex thing. What I think is amazing are these Falcon 9s that they get the boosters and they bring the boosters back to the surface of the earth from way out there, and they land them on a barge out in the middle of the ocean somewhere. I find that amazing that they can do that. So velocity doesn't always change uniformly. So we got stuff to talk about. So kind of like in this Transformers movie, this is one of my favorite Transformers. My father was the first wheel. And what we're going to do next time, so we are going to dismiss a little bit early today. Next time we're going to discuss Newton's laws of motion. So if you have the textbook, go ahead and read up on that. All right. And one more thing. I forgot to put a slide in here about homework. I'm going to give you some more homework over the weekend, and it will be ready to go by lunchtime tomorrow, if not sooner. Okay, you're dismissed. Come on up here to the front if you want to check your iClicker.